Hello everyone, welcome to our paper presentation. Our presentation is titled as Aggregating Learning Agents for Microgrid Energy Scheduling During Extreme Weather Events. I am Avijit Das. I am working as a postdoctoral research associate at Pacific Northwest National Laboratory. I did this work during my PhD study when I was at Florida Atlantic University. Today I am going to present on behalf of my team. So first, let's talk about the background of our research work. The increasing threats of weather-related incidents and natural disaster highlight the urgency of considering resiliency in scheduling operation. If we see the statistical data, we can observe that natural disaster is one of the major cause for power outages. Only in United States, out of top 10 biggest blackouts, 9 of them due to extreme weather events and 8 occurred after the year 2000. These events also have annual impact like 20 to 75 billion. Microgrid Microgrids can be a viable solution to address these challenges, and microgrid also successfully participated in different extreme weather events. With the ability to work in both grid-connected and isolated mode, microgrid can significantly enhance reliability and resiliency, also improve the efficiency, and it can provide cleaner and cheaper energy, enabling diverse distributed energy resources. Since microgrid has like diverse distributed energy resources, so scheduling is very important in order to minimize the economic loss and also power interruption time. So it is very important to consider resiliency during microgrid scheduling operation. These slides present the problem formulation of the microgrid scheduling problem. We formulate the problem as a Markov decision process. So here we have the state information. For the state information, we consider like battery, renewable generation, grid price, and load demand at time t. And for the decision variables, we have like battery charging, discharging, power output, diesel generator power output, and also power exchange between microgrid and main grid. For defining the cost function, we have like two different cost functions. Like diesel generator cost is a like quadratic cost, and where we have like x, y, and z. Those are like fuel cost curve coefficients, and we also consider diesel generator on-off status. For defining the microgrid revenue, we have considered like power exchange and the grid price. So here the objective is to minimize the total operational cost of the microgrid. So here our goal is to find the optimization policy that will minimize the total operational cost of the microgrid subject to microgrid operational constraints. These slides present our proposed learning approach for microgrid scheduling with resiliency consideration. We propose an reinforcement learning approach with parallel local agents. So here the parallel local learning agents, they are interacting with different microgrid operating conditions. So here we have considered like two different microgrid operating conditions. One is normal operation and another one is emergency operation. For defining emergency operation, we have considered like 4 hours of power interruptions in the time frame according to USEIA data. In USEI data, we found that like on average 4 hours of power interruption happened during major events. So we have considered that in our case studies. So if you see in our proposed design, local learning agents, they are interacting with different microgrid operating conditions in a distributed way, and also they are updating their optimization policy, and then they are reporting to the global agents probabilistically. In compared to the traditional multi-agent reinforcement learning approach, instead of having only one queue table or queue network, here we have queue table for all the agents. So here the local learning agents, they are interacting with their own environment and learning their optimization policy and updating their value functions, and those value functions are used to update the value function for the global agent probabilistically. So this is the equation for updating the Q value function, and here we are considering learning rate alpha and also microgrid instant cost to update the Q value functions. For updating the Q value function for the global agent, we have considered this equation where Qg is representing the Q value function for the global agent. Q and R is representing the Q value for the normal operation, and P is representing the probability of having outage, and QEMG is representing the Q value function for the emergency operation. And here Q small st is representing the set of states at time t. So learning like different microgrid operating conditions and updating the global agent with a probabilistic manner, we are expecting like global agent should learn all the microgrid operating conditions in a effective way and perform better like in terms of microgrid scheduling. For the experiment, we have done two different case studies. In case study 1, we have considered 70% of outage probability. For defining the emergency event, like we have assumed like power interruptions happen at hour 4 to 7. So here we summarize our result. If you see the result in terms of expected total cost, our proposed approach can reach very close to the optimal solution. And also if you see the convergence curve, like the cost curve of the proposed approach, it drops rapidly and converges close to the optimal solution in compared to the existing reinforcement learning approach. We have also provided the power output of the decision variables. If you can see, like since we have very high outage probability, our proposed approach is utilizing the diesel generator instead of taking power from grid to supply the load demand. In case study 2, we have considered like 30% of probability of having outage. So in this case as well, like if you see the results, in terms of expected total cost, our proposed approach can reach close to the optimal solution. And the cost curve shows that our proposed approach outperforms the existing reinforcement learning approach. And here also we provided the power output profiles from the global agent. So here I want to add that like since our local learning agents, they are learning the optimization policy in a distributed way, microgrid operator can also have the access to get the optimization policy from the local agents. In that case, like even though we have like low outage probability, if needed, microgrid operator can also get the microgrid scheduling decisions from the local agent. In conclusion, in this paper, we propose an reinforcement learning approach with multiple parallel local learning agents to efficiently solve different microgrid operating conditions. And our results show that our proposed method shows around 10% of improvement compared to the existing reinforcement learning approach and can provide better optimization policy through distributed learning. An interesting future work would be handling renewable generation randomness and also solve real-time optimization problem considering uncertainties. Thank you.